Hello, welcome to the presentation by Group 11 on power analysis attacks and their mitigation techniques. In this group, the members are Gunjan Dhanuk and Pranjal Singh. So, a brief introduction about power analysis attacks. So, side channel power analysis attacks were first introduced by Kosher in late 1990s. These kind of attacks exploit the correlation between power consumption of a device and the operations performed by it. So, by just seeing the power output traces, we can correlate if a particular operation is taking place. For example, if there is an addition and multiplication operation and the multiplication consumes a higher power, we can see from the power output if there was a multiplication or an addition going on in a particular cycle. And this information can lead to revealing sensitive information like cryptographic keys or algorithms. This form of attack has evolved considerably over the years, prompting extensive research into both how to come up with sophisticated attack methods and also to come up with stronger defenses against those kind of attacks. So in this survey, we are considering three papers based on attacks and their mitigations. The first paper is called An Inside Job, Remote Power Analysis Attacks on FPGAs. So this paper challenges the conventional understanding that power analysis attacks require physical access because they are able to do such an attack with no physical access remotely. The second paper is Lock and Roll, which shows a deep learning power side channel attack mitigation technique using new and emerging reconfigurable devices and logic locking. The third paper is a cryptographic measure with random dynamic frequency scaling to mitigate correlation power analysis attack. So moving on to the first paper.
Yeah, so the first paper is an inside job on remote power analysis attack on FPGAs. The main idea behind this paper is introducing the idea of exploiting the internal sensors within an FPGA to perform power analysis attacks remotely. So this paper uses the internal sensors within a system to trace the power output of the system, unlike the conventional approach of using external sensors outside a system, and thus it does not require the physical access to a system, which is a general requirement for side channel attacks, especially power analysis attacks. So the fluctuations that they obtain from the internal sensors are indicative of the computations taking place and can be used to extract sensitive information. So using the internal sensors, the information that they obtain can be used to draw conclusions about the activities taking place inside the system, and thus can be used to reveal sensitive information. So let's look at the methodology followed by the researchers. So the model they propose utilizes the programmable nature of FPGAs to create internal sensors capable of monitoring dynamic changes in the FPGA's supply voltage. Now, in an FPGA system, the users are capable of creating internal sensors inside the model. So the attacker tries to create sensors close to the AES module so that it can trace the changes taking place to the FPGA's supply voltage and use it to draw various conclusions about what is happening inside the system. The implementation involves setting up these internal sensors close to the cryptographic module and conducting CPU attacks on it, which can be done remotely. So the implementation involves, can we go back? Yeah. So the implementation involves the attacker tries to set up these internal sensors as close to the cryptographic module as possible so that he can perform the correlational power attacks on it. And this can be done remotely as the FPGA systems provide remote access. Yeah. Let's look at the key results of this paper. So firstly, it shows how internal sensors developed within an FPGA can successfully retrieve the secret key from an AES encryption module without physical access. So the people tried to use the internal sensors within an FPGA and they could successfully retrieve the secret key from an AES encryption module without any physical access, and thus channel the traditional approach of the necessity of having a physical access to the system for performing power analysis attacks. Uh, It also showed how the internal sensors can be used just as powerfully for power analysis attacks as the traditional ones using external measures. So the researchers did not use any external sensors around the system to trace the power consumption. Instead, they used the sensors within the FPGA system, and thus they showed how the internal sensors can be just as powerful as the traditional external sensors used for side channel attacks. The advantage of this paper is it introduced a new class of side channel attacks that do not require physical access relevant in cloud computing and shared FPGA based systems. So the new class of side channel attacks that they introduced do not require any physical access, and in today's world when cloud computing and shared FPGA based systems are becoming very common, these attacks are very important and relevant. The limitation of this paper is the efficacy of the attack heavily depends on the ability to implement effective internal sensors using the FPGA primitives. So setting up internal sensors in an FPGA system can be problematic for an attacker, and this majorly limits the approach used in this paper. Let's go to the next paper.
So the next paper is lock and roll. This is a deep learning power side channel attack mitigation technique, which uses new kind of reconfigurable devices and logic locking. So let us go into more detail about this. The main idea of the paper is to address the increasing security concerns that are associated with ICs due to the globalization of the semiconductor business model. So since the chip is now manufactured in various places, each having their different IPs, so there is no trust between different parties on what are the internal components. So this method, lock and roll, uh, develops a multi-layer defense mechanism in which they use magnetic random access memory (MRAM) based lookup tables, which they call SIM-LUT, for mitigating both PSCA, which is physical power-based side channel attacks, and SAT attacks. So the method for this paper, first of all, they developed this SYM-LUT, which is designed to resist ML-assisted power side channel attacks. So they've specifically targeted the ML-assisted attacks, and to mitigate those attacks, what they have done is they have achieved near zero power variation in the outputs. So the attacks that initially used the variation in power to judge the operation could no longer do so. To achieve this, SIM-LUT employs a magnetic tunnel junction (MTJ) to create a reliable low overhead LUT, which is a lookup table, with a wide read margin, which is very crucial for LUT-based obfuscation. So at the lookup table level, the outputs are obfuscated, which means the outputs are not clear enough for any attacker to draw any conclusions. This SYM LUT is also complemented by a scan-enable obfuscation mechanism, or SOM, which enhances the overall security, hence providing a multi-layered defense for ML-assisted attacks. The key results that were presented in this paper are, first of all, they noticed that since SYM LUT has a small overhead as compared to the traditional static random access memory model, but still it was able to prevent against those particular attacks, and hence they believe that this is a better approach. They also measured the energy consumption of this type of a circuit, and that is mentioned in the paper, and empirical evaluations using machine learning assisted techniques. So they tested it specifically against machine learning based attacks, showcase the difficulty in reverse engineering the contents of the MTJs, the magnetic tunnel junctions. Hence, these cannot be reverse engineered so easily. So breaking them is also very difficult.
So let's go to the cryptographic risk we associate with RDFS countermeasure paper. This paper presents a new countermeasure against side channel power attacks. Next slide. The main idea behind this paper is it tries to address the vulnerabilities of cryptographic SOCs to power analysis attacks. So this paper is basically focused on addressing the weaknesses in the cryptographic systems against power analysis attacks. It introduces a random dynamic frequency scaling countermeasure which aims at significantly improving the resistance of cryptographic SOCs against these attacks. This method basically means that it dynamically changes the working frequencies of the cryptographic systems and tries to obfuscate the information to prevent side channel power attacks. Let's look at the methodology of this paper. The RDFS countermeasure operates by generating a vast number of distinct frequencies, more than 219,000, specifically for driving the cryptographic accelerators within the SoC, thus discouraging power analysis attacks. So basically, the RDFS countermeasures, it generates a large number of frequencies, approximately 220,000 frequencies, which are then used for driving the cryptographic accelerators present on the system on chip. And this tries to discourage power analysis attack. The RDFS countermeasure allows the AES-128 accelerator to operate a wide range of frequencies between 50 to 100 megahertz, and these frequencies are chosen by an on-chip pseudo-random number generator. So this countermeasure, they implemented it on an AES-128 accelerators, and it allowed the accelerator to work on a wide range of frequencies between 50 to 100 megahertz. And these frequencies were generated using a pseudo-random number generator, thus ensuring that the frequency generators were random and uniformly distributed, making it difficult for the attacker to detect any pattern or to draw any conclusions about what frequencies would be chosen next. And thus this could hide uh, the information from any attacker. Let's go to the next slide. Some key results of this paper. The RISC-V SoC, when protected by RDFS countermeasure, showed remarkable resistance against CPA attacks and TVLA tests, and also increased resistance against the DLSC attacks. So basically, this paper, when the RDFS countermeasure was introduced in the RISC-V SoC system on chip, it showed remarkable resistance against the correlational power attacks. In fact, up to 5 million traces, the attacker was not able to find out any useful information about the working of the system on chip, and it also increased the resistance against the deep learning based side channel attacks. Thus, it is a useful countermeasure that can work on a variety of attacks. Now look at some advantages and limitations of this paper. So an advantage of this paper is it enhances the cryptographic SoCs without incurring high performance overhead or additional hardware costs by leveraging the capability to dynamically reconfigure operating frequencies. So the approach of this paper is about reconfiguring the operating frequencies of the cryptographic module of a system on chip, which does not require any high performance overhead or additional hardware costs. Thus, at a low cost, it provides a high protection against side channel power attacks. One limitation of this paper is it cannot completely prevent any deep learning based side channel attacks. In fact, the state of the art deep learning based side channel attacks can still break through this countermeasure.
So in conclusion, we overviewed the current trends in power side channel attacks and the state-of-the-art techniques employed to mitigate these threats. So the first paper, Inside Job, exemplified the evolving nature of power side channel attacks by showing that such kind of attacks can not only be conducted physically but also remotely on FPGAs. The second paper, Lock and Roll, reflects a trend towards integrating more integrate and layered defense mechanisms. For example, they use the lookup table and magnetic random access memory in hardware design to combat advanced side channel attacks like the ones based on machine learning. The third one is the RISC-V SoC paper, introduces the RDFS countermeasure, which represents a trend in employing adaptive and non-static defensive strategies. That is, keep the frequencies continuously changing, acknowledging that static defenses might no longer suffice in the face of sophisticated attacks. So this was our presentation on power analysis attacks. Thank you.